Hi, this is Chintan Patel. In this lecture, we are going to see few concepts related to bending stresses in beams. Whether this concept is related to, is not only related to the civil engineering, but it is also useful for the mechanical component designs. For example, our gear design is assumed to be done using the concept of the cantilever beam. And that's why the bending stresses generated in the beam are equally important for the civil engineer and as well as the mechanical engineer. So many components are going to be, we are going to design so many components using these concepts, and that's why you need to understand this concept thoroughly. Let's get started with the first slide where we will see a definition regarding the bending stress, and this is nothing but one type of assumption, and that is the definition of the pure bending. So what is pure bending and what is pure bending stress? Okay, so let's explain this condition. When a beam length is subjected to a constant amount of the bending moment and a zero shear force, then the stresses set up across the cross section of the beam due to the bending is known as a pure bending. Now this is the pure bending condition. As you can see in this diagram, a small length of the beam having the dx distance is considered into the beam, where both the sides of the length is subjected to the bending moment only, where no stresses are or the shear forces are introduced onto the beam. So this is the condition we need to assume into the every theories of the bending stress. Whenever we are going to derive any equation into this chapter, we will assume first that this condition is going to be applied into that theory or any example where we are going to apply these concepts. Okay, so first of all, we are assuming that the beam is subjected to the pure bending conditions only. There is no shear force acting on the beam and there is no other stresses acting on the beam. So there might be different kind of a stresses generated due to the different conditions, but the bending stress is generated due to the pure bending conditions only. There is no other stresses which comes into the picture of the bending stress theory. Okay, so pure bending condition is one of the assumptions that we are going to use during the derivation of the theory, as well as whenever we are going to calculate the examples based on this concept, we are going to use this kind of assumption. Okay, in the real world, there may not be this kind of a condition occurring during the working condition, because the pure bending always comes with the shear forces, a little bit amount of shear forces and a reaction into the beam, and that's why the reactions generates the shear forces, and shear forces itself generates the shear stresses. So in the working condition, you may find a different kind of a shear forces which will violate the condition of the pure bending. Okay, so let's get started with another slide. In the next slide, we will see one theory regarding the assumptions in the theory of the pure bending. Now, what are the assumptions? That I've already explained you the one assumption regarding the pure bending condition. But there are also few more assumptions which will help us to simplify the working condition into the pure bending scenario. Okay, so that we can derive the equation of the pure bending and easily calculate the bending stress which can be generated into the beam during the pure bending condition. Okay, so we will see those assumptions right here. As you can see, the first assumption itself indicates that the material of the beam is homogeneous and isotropic. That we are assuming that the beam is made up of the material which is homogeneous and isotropic. Now, what do we mean by the homogeneous? Homogeneous means that the material is having the same kind everywhere throughout the beam. Whether you are finding the properties at the top of the top corner or you are finding the properties at the bottom corner, each and everywhere of the beam, wherever you go, you will find the same kind of the material throughout the beam, and that's why this kind of a material is homogeneous. Now, what do we mean by the isotropic? Now, directional properties like the elastic properties are the same in all the direction. we have assumed that the material is isotropic, which indicates that your material is having the directional properties in all the direction same. Like which kind of a directional properties? Elastic properties. Elastic properties are going to change with respect to the direction. If you go in the left side right direction, in the left side horizontal direction, you will find another properties. If you go right side horizontal direction, you will find another. If you go vertical, it will be different. But we are assuming that your material is isotropic, and itself indicates that your directional properties like the elastic properties are going to be constant in all the directions. Okay, so this was our first assumption. Now we will move on to another assumption, that is the beam material is stressed within the elastic limit, and that's why the Hooke's law is applicable. And this is the only way by which you can apply the Hooke's law and the basic equations of the stresses. Why we are going to use this kind of a stresses? Because first initially we need a very simplified form of the bending stress equation. Later on we can add a few more constraints and constants that can amplify our simple condition into the complex working condition. Okay, so these are the basic terms where we need our Hooke's law theorem which needed to be applied, and that's why our each and every forces or the bending moments and the loading conditions are going to be within the elastic limit. If they go beyond the elastic limit, then you won't be able to apply the Hooke's law, and that's why it is necessary that we assume this assumption. Now we will see another assumption, that is the transverse sections. First you need to understand what is transverse. Now any direction which is along the length of the beam is longitudinal. I am introducing two terms, longitudinal and transverse. The first term is longitudinal. Now consider a length of the beam. Most probably the beams are horizontal. Okay, so these beams are having their length in the horizontal directions. So the horizontal direction itself indicates the longitudinal direction. But what is transverse direction? The direction which is perpendicular to the longitudinal direction is known as a transverse direction. So if your beam is having the horizontal longitudinal line, a longitudinal direction, longitudinal axis, then the vertical line or the vertical axis will be your transverse axis. In the transverse direction, if you are having the plane sections before the bending, then they will remain the plane even after the bending. Due to bending, there might be the deformation into the whole body of the beam, but the beam is not going to deform that much that your plane sections which were plane before the bending are going to distort. They are not going to distort, they will remain the plane section even after the bending condition, okay, or even after the deformation due to the bending. Okay, so this was our third assumption. Now this third assumption can be possible only if you assume the fourth one. Now what is the fourth one? The fourth one is the transverse section. Fourth one is the reason for your transverse section to remain the plane. Now what is the fourth assumption? That is that each layer of the beam is free to expand or contract independently of the layer above and below it. Now what is this assumption? Let me explain it a little bit clearly. This assumption indicates that we are assuming that our beam is made up of the number of layers. Okay, so the thickness of the beam is made up of the number of layers, and each layer is free to expand or contract independently with respect to the another layers. Whether it is in the middle one, it is free to expand or contract as independently from the above and the below layers. Okay, so this was the basic assumption that you need to assume. Otherwise, your third assumption will fail if you don't assume the fourth one. Okay, now we will move on to the next one, that is the value of Young's modulus is the same in the tension and compression. There is a little bit change in compression and the tension because some materials are more tough during the tension, but they are more soft during the compression. So there may be the changes in the properties of the elastic properties during the compression and the tension based on the material, But whatever material we are considering for the manufacturing of the beam, we assume that the elastic constant for that material will be the same in the tension and compression. Okay. Now we will see another assumption, and that is the last one. Congratulations. That is the beam is in the equilibrium, i.e., or it means that there is no resultant pull or a push force in the beam section. I have already told you this this assumption where in the definition of the pure bending, where we assumed that there is no shear force or the zero shear force is acting on the beam, and only the bending moment is acting on the beside the beam, which is causing the bending of the beam. And that's why if there is no shear force or the resultant shear force is zero, then the resultant or the total pull force or the push force, pull and push, that are the different terms for the tension and the compression. So the summation of the tension and the compression force are zero, and that's why your beam is going to be in a equilibrium. So this was all our assumption that we are going to apply in our theory of the bending stress. Now we will see another definition which comes into the picture whenever you are going to give the examination of this chapter. The one of the favorite definition, that is the neutral layer or a neutral plane. Now what is neutral layer? As I said earlier in the assumption part, that the beam is made up of the number of layers. Beam is made up of number of layers, and there might be the changes into this layer because those layers are independently free to expand or contract, and that's why they may expand or contract. Okay. Now if you assume this kind of a theory, then you need a diagram like this. Okay. So if you see in this diagram, whenever you apply the bending moment onto the beam, after the bending, the beam is going to deform like this, like a curvature. Okay. So if you can notice in the curvature, there is a line, upper line denoted by the A dash C dash. This upper line is getting compressed a little bit. Okay. This upper line is getting compressed. Its length is getting reduced. But if you notice the lower line, that is B dash D dash, this lower line B dash D dash is getting stretched, or its length is getting increased. So that's why we can say that the lower line B dash D dash is getting elongated while the A dash C dash is getting compressed. Okay. But there is one middle line that is R dash S dash. R dash S dash is also deformed in the curvature manner. But if you notice that the R dash S dash length is negligibly changed, or we can say that its length is remaining constant, and that's why the layer R dash S dash line represents the layer. You are seeing this view from the front side, but if you see in the top side, that R dash S dash itself indicates the complete layer of the beam, and this complete layer is having its length unchanged or a constant, and that's why this layer is neither in the tension side nor in the compression side, which indicates that this layer is a neutral layer, or we can say that it's a neutral plane. So this is very important definition, because you need to identify this layer first, then you will be able to draw the bending stress diagram, bending stress distribution diagram. Otherwise you will be failing drawing this kind of a diagram without identification of the neutral layer. Now, as I said, the length of the neutral layer is remaining unchanged, or the length of the neutral layer is constant. It indicates that there is a zero deformation or a negligible deformation into the neutral layer. If the deformation is zero, then the layer is not going to induce any resistance regarding that. And if there is no resistance into the neutral layer, there will not be any bending stress generated into that layer. So we can say that due to zero deformation or negligible deformation, a neutral layer is having zero bending stresses into it. So this was our first layer which you need to identify. Why? Because this is the layer where you will find a zero bending stress. above the layer and below the layer there will be the different nature of the stresses, because above the layer you will find the tensile bending stress and below the layer you will find the compressive bending stress, but the nature is changing only and the value is going to be the zero at the neutral layer. Okay, so this was very important layer. Now we will see another derivation that can be asked in your examination into the 5 to 7 marks, that is the equation of bending stress. They may ask you differently. There are a lot of methods of asking this kind of a question, but they can ask you this question into the 5 to 7 marks. Depending on the marks, you need to explain the length of your answer. You need to decide the length of your answer. Now, if you can see this diagram indicates two different conditions. The above diagram or the upper diagram indicates the before bending condition, and the lower diagram indicates the after bending condition. These are two diagrams but of the same beam. Now consider a strip PQ above the neutral layer RS. Okay, consider a strip PQ above the neutral layer RS. This PQ strip is having the length of the dx. Okay, its thickness is a very small, so we can consider it as a rectangle. Even after the bending condition, it will remain the rectangle because its thickness is very small. Okay, it's an elemental strip, and we will derive an equation for it, and then we will integrate it for the rest of the part of the beam. Okay, so this is our method of derivation of the bending stress. Now consider that small length dx of the beam subjected to a bending moment as shown in a figure. Okay, as the result of the moment, a small length of the beam bent into an arc of the circle with O as a center. As you can see in the lower diagram, we have represented the deformed beam in the arc manner, and arc is having its center at the O point. O point is represented at the R radius at the top. Okay, now M is the moment acting on the beam, theta is the angle subtended at the center of the arc, center by the arc, radius of the curvature is represented by the R. Now remember that figure, we will see in the next derivation steps. Now the rest of the derivation steps are like this. Consider a PQ. As I said, we need to consider an elemental strip PQ at a distance of the y from the RS. Now what is RS? RS is again a neutral layer, and you need to identify this neutral layer because this is the layer where the bending stress is 0. So the RS is the neutral layer or the neutral axis of the beam. Let this layer be the compressed to P dash Q dash. Now if you apply the bending moment, then your beam is going to deform, and due to the deformation your beam will deform like this, like an arc, and above the neutral layer you will be compressed, or each and every layers will be compressed, and below the neutral layer each and every layers will be stretched. Now we are considering this P dash Q dash which is compressed. Okay, now we know that the length of the P dash Q dash is reduced from the PQ, so the change in length can be calculated using the delta L. Okay, so we have denoted it as a delta L. So delta L is equals to PQ, that was the original length, and which is compressed to P dash Q dash, and that's why delta L can be written as a PQ minus P dash Q dash. Okay, now if you want to find out the strain, now what is the strain? Strain is nothing but the ratio of the change in length upon original length. Now we already found the change in length, that is delta L. So delta L upon original length. What was the original length? The original length was a PQ. Now what we are going to do? We are going to substitute the value of delta L. So what was the delta L? PQ minus P dash Q dash. So PQ minus P dash Q dash upon PQ. Now if you divide this equation individually, you will find 1 minus P dash Q dash upon PQ. Now we will try to find the P dash Q dash upon PQ. How? By applying the similarity rule of the triangle. What is the similarity rule of the triangle? First you need to understand which similarity rule and where we are going to find this rule. First of all, I will use some annotation to indicate the two different triangles. The first triangle is nothing but this triangle. I am denoting it with the red line. Okay, so this was our first triangle where the apex of the triangle is the O point and the base of the triangle is P dash Q dash. So this is our first triangle in the, and this is the smaller triangle. Now we will consider another one which is similar, to which we can apply the similarity rule between those two triangles. Now as you can see, the apex will be the same for the second one. Okay, so apex is the same, it's O. Now I will draw another line up to RS, So, and the base of that triangle would be R dash S dash. Okay, so this is another triangle having the base as R dash S dash. Both the triangles are having their apex at the O point, but both the triangles are having the two different bases. The first triangle is having the base as a P dash Q dash, and the second one is having the base as the R dash S dash. So these are the two triangles where we are going to apply the similarity rule of the triangles. So how this similarity rule is going to apply in this equation? As you can see in this equation, P dash Q dash, that was the base of the first triangle. R dash S dash, that is the base of the second triangle, is equals to R minus Y, that is the height of the first triangle, upon R, that is the height of the second triangle. Now if you just subtract this equation from the 1 on the both the side, then you will get the answer as a 1 minus P dash Q dash upon R dash S dash equals to 1 minus R minus Y upon R. Now if you take the LCM, then by taking the LCM you will get that R dash S dash minus P dash Q dash upon PQ is equals to Y by R. This is our final equation. Now what we are going to do, we are going to put the PQ in place of the R dash S dash. How we can say that these are the same? How we can substitute this? As we know that the PQ length was equals to R dash S dash length. How we can say that? Because R dash S dash is the length of the neutral layer, and the length of the neutral layer, it gets unchanged, or its length is remaining the same. So R dash S dash is equals to R dash RS, and RS is equals to what? PQ. So we can directly put the value of PQ in place of the R dash S dash. Okay, that's why we are putting the value of the PQ in place of the R dash S dash. Now if you see this equation is somewhat like this one equation where we have calculated the strain of the member. Now if you compare those equations, you will find that the strain epsilon is equals to Y by R. This is our final equation. Now we know that the relationship between the stress and the strain, the relationship between the stress, that is bending stress due to the bending, is equals to strain into elasticity, that is epsilon into E. Now if you make a subject epsilon, you will get the answer as a sigma by E, and by putting this value into the above equation, you will get the equation as a sigma by B equals to Y by R. So this is our final equation from this first section. So Y by R is equals to, upon E is equals to this one. Now if you simplify this equation, that sigma B by Y equals to E by R. This is our equation number 1. This is a final equation. From this equation you can easily identify the value of the sigma B, where you can make it as a subject. Now we will see the rest of second part of the equation. The second part of the equation is a little bit easy, where you will find the cross section view, and this is the cross section view of the beam. Now as you can see in this cross section view, the length is given as a Y. Now our interest is to find out the moment. Now we need to find out the moment. Let's consider the area of this PQ. The area of this PQ is delta A. Okay, so this is the area of the PQ. Now we have the value of a stress from this equation. We have this value directly put over here. Now if you know this value of the stress, and if you multiply it with the area, what will you get? You will get the value of the force. Okay, so this is our force, and force into distance will give you the answer of the moment. So our intention was to find out the moment, and we got the moment by multiplying the force into distance. Okay, so this is the moment of the only elemental strip, but we need the moment of the whole entire section. So that's why what we are going to do, we are going to sum the sum of this kind of elemental strip moments, and at the end you will find the sum of the y square into dA, which is nothing but a moment of inertia. This term can be represented as a moment of inertia, area moment of inertia, both are the same. So area moment of inertia is represented at this level. Now if you simplify this equation, it will look like this, and this equation can be easily compared with this equation, the first one. And if you compare this equation, you will get the final bending stress equation like this. This is the bending equation, and believe me, this is the only equation using which you can calculate the examples of the bending stress. So this was very important derivation, and it can be asked in your examination into the 5 to the 7 marks. So you need to remember these steps, and based on those steps and concepts, you will see the examples in the upcoming lectures, and we conclude our lecture over here. Thank you.